All right, we have another daily problem. 590, N-ary tree post-order traversal. Given the root of an N-ary tree, return the post-order traversal of its nodes values. Um, Yep, and then N-ary tree input serialization is represented in their level order traversal. Each group of children is separated by the null value. See examples. You don't really need to worry about that because that's not how the code is going to interpret it. You know, it's not. You're not given an array. You're given one root node, and then those root nodes have pointers to its children. So no stress about that. I really wish that instead of describing that, it would describe what post-order traversal is talking about, because this is described as an easy problem. And I think that an easy problem should be given an easy description. Yeah, you can look up what post-order traversal is and it'll cause you to learn, but why not have this all right here? I think you really have to focus on accessibility and making sure that, if you're new to coding, that you know what they're talking about. Otherwise, you might get disillusioned and you might get discouraged. So, I don't know. But yeah, so today's problem is pretty easy, and it's even easier if you've done yesterday's problem. In fact, this might be the easiest one yet as a result. So, post-order traversal, let's go over that. I have this right here. It's just a little quick website that describes it. So you traverse through, the core of it is left to right children, and then the root. And then that's recursive. All right? So you do the same thing so you do that same logic for its children. So left to right, then the root. Here's the example with a binary tree. We go left to right, and then root. But left, we do the same thing. Now starting with 2, we go left to right, and then root. So now, since 4 has no children, we can add that we can have that be the first in our traversal. Then we go right, and then root. All right, and then we go back to 1, and then remember we did left to right, so now we did the 3. 3 has no left, so we go to the right, we get 6, and then we get the 3, and then root. 1. Left to right, then root. So this is what the solution looked like yesterday. We have a little helper recursive function because we want to we want to recurse through, but all the while accumulate up a list. And we need to make sure that the helper function allows us to be editing the same array even as we recurse through the tree. Because if we were to call the same function, but this was inside this function, or if we didn't have the helper function, then we would be resetting that array every time. It's just easier this way with that global access. Not global, but yeah, what's it called? Function scoped. Yeah. Or block scoped? Yeah, I don't know. So it's, yeah, as straightforward as it gets. Yesterday's solution was pretty good. We did pretty good. Yeah, 23 milliseconds on runtime. Yeah, dang. Yeah, that's. I don't think I'm ever gonna do better than that, to be honest. I think I also just got lucky. But yeah, so just to go through yesterday's, we traverse the left, then we traverse the right, and then we append the value that we're on. And then we just run that recursion starting from the root, and that adds to this array over time. So yeah, it's left, right, root. Okay, and that first left, and then we do the same thing, left, right, root. Simple as that. So now we just need to make one little edit to make it work for multiple children instead of, well, more than 2 children. We're going to do the exact same thing. Traversal equals an empty array. Define traverse node. Okay? We're going to say traverse. Oh, yeah. Yeah. Let me do n for node. No, n could represent number. What do you say node? Okay, if node. Okay, this is the if node will make sure that basically it stops the recursion once we reach the end of the tree. Because remember, we're going to recurse through this. So when we get to 4, we say, okay, now try to do this on its left and right children. So we try that, but there's nothing. So we don't do that. And I like, you could check to see if that's children before you recurse rather than recursing and then checking if that children exists. Well, if that child exists. But I like this because this deals with edge cases, like if you're handed no node at all. Because if you're handed no node at all, then you don't start by saying, okay, check the children, and then you run into a bug because it's like, the children of what? Okay. I also love recursive problems because I sound like a crazy person when I try to word what I'm saying. Okay, so if node for, it's the same thing as yesterday, only we need to do it for more than left and right. For child in node.children. If there's none, then this just won't run. So that's good. If node for child in node.children, traverse child. Okay, then once we're done traversing all the children, same thing as yesterday, except instead of left and right, we're traversing all the children. We're going to add that the value of the one we're on to the recorded traversal of the tree. Okay? Now, we just traverse the root, and then we just return traversal. Okay? Initialize, so I'm going to comment out this code just to go through again. So we're going to initialize the traversal recording, set up recursive helper function, check that node exists, iterate through children. Oh, I need to, iterate through children and recurse through them. And then after going through children, add self. Okay? Start recursion, return results. Let's see if that works. Yes, it does. Does it work for all of them? Yes, it does. Awesome. Way to go. All right. That's today's problem. Yeah, pretty straightforward, pretty enjoyable. I wish the description was a little bit better, but, you know, it causes you to have to look things up, read some literature. All right. Thank you so much for watching. And, yeah, I'll hopefully see you tomorrow.